We're back for another round. We have to get back to our beginning. So, we ended with our reference table. Sun is dipping lower in the sky. We ended with our reference table. And we begin with this beautiful image of the space shuttle coming back to Earth after a trip to the International Space Station, or it just was going around the Earth, around and around and around every 90 minutes, one trip. And I always like this image because it kind of gives you a sense of the layers, the troposphere, because it's not too bad in terms of scale. The troposphere, a very thin layer at the surface, stratosphere, where the ozone is, mesosphere, endothermosphere, and exosphere. So while it's not exactly correct in terms of how one would interpret the layers here, it gives you it's a nice visualization of those layers. Energy in the atmosphere is our next subject. All energy in the atmosphere is something what you already know about. It's delivered by the radiation of electromagnetic waves. Visible light and radio waves, as we know, reach the surface. UV is absorbed in the stratosphere, except for a little bit. A little bit of infrared reaches the surface. But most of that microwave and infrared are absorbed in the stratosphere. X-rays and gamma rays can be deflected if they were to escape the sun, but many of the X-rays and gamma rays are actually absorbed within the sun. And high energy particles from the sun can reach the poles, drawn in by our magnetic field if they're charged particles, if they have a positive or a negative sign, and they can create beautiful auroras in our atmosphere. And we remember this diagram, right? So our shortwave radiation, except for a little bit of ultraviolet, is blocked from entering the atmosphere. Our visible all enters, a little bit of infrared, maybe a little bit of microwave right at the border of the radio wave size, lots of radio waves. Now, the atmosphere is in radiative balance. What does that mean? What we want to try to express there is that over time, the Earth has had a balance, particularly over the last several, million years, where the amount of heat entering, being absorbed when the sun is out during the day, is balanced by the amount of heat that's able to escape, plus the amount of heat that is trapped in our atmosphere by what are known as greenhouse gases. If this weren't the case and we had a net gain, the Earth would continue to heat up and it would eventually be too hot for life. If we lost too much heat at night, the Earth would continue to cool down and it would be too cold for life. So we need this radiative balance with some seasonal net losses and gains. But overall, the expectations for what has happened on the Earth, as we read it in the record of rocks and other ways in which we can determine the climate conditions of the Earth in the past, shows a very stable atmosphere in terms of temperature. But we also know that if you change the amount of what are called greenhouse gases in the atmosphere, you can warm the atmosphere if you have more of them, and you can cool the atmosphere if you have less. And what we have seen since the major exploitation of fossil fuels by human beings in the 19th century, we have seen a steady increase in carbon dioxide and methane, two greenhouse gases in our atmosphere. It's not in balance. So in general, you would have incoming solar radiation, some of which would be reflected by clouds back up out of the system. You would have some reflected by the surface. You could also add that the surface reflection is both from ocean and from ice, which is very important. So the more ice you have, the more reflectivity. Then you have a certain amount of energy released at night on the dark side of the Earth, some of which is being emitted by clouds where water vapor is condensing and releasing heat, and it goes back up towards space. But greenhouse gases right here will absorb a percentage of that which is emitted from the surface, and it will radiate that heat back. You also have air, which is rising due to daily heating of the earth, and then again the change of state, which is that which is emitted by clouds, the release of latent heat, which is something we'll learn about as this unit on the atmosphere, weather, and climate continues. So what are greenhouse gases, and what's the greenhouse effect? We should know this because it's a huge part of your reality, my reality, the reality of the Earth. Naturally occurring gases that absorb infrared radiation emitted from the dark side of the Earth that warm the Earth. That is a definition of greenhouse gases. The major greenhouse gases that we are concerned with are carbon dioxide, naturally occurring, methane, naturally occurring, some naturally occurring chlorofluorocarbons, but those are mostly human-made, ozone, mostly human-made, and some nitrous oxide. The two important naturally occurring are carbon dioxide and methane. So as we already showed, some energy is absorbed by the Earth from the sun, some is bounced back. Greenhouse gases are important in absorbing energy that keeps us warm, because if we didn't have these greenhouse gases, the Earth would be too cold for life. So here's a simple diagram I drew one year on a whiteboard with visible light, right, in a certain wavelength from, say, 580 to, I can't remember the wavelengths, maybe was it 500 to 700 nanometers, something in that zone, from the sun, striking the Earth during the day. But at night, infrared radiation, longer wavelengths of infrared, are released from this warmed Earth, warmed by the visible light. And in the atmosphere at night, greenhouse gas, carbon dioxide, water vapor, I didn't mention that, it should have been mentioned in the other slide. Water vapor is a powerful greenhouse gas. Methane, CH4, and this nitrous oxide can absorb the heat and hold it close to the Earth, like a blanket. If you had no greenhouse effect, as I said before, the average surface temperature would be 255 degrees Kelvin, negative 18 degrees Celsius, or 0 degrees Fahrenheit, the average temperature. Right now, the average temperature is 15 degrees centigrade. So we need these greenhouse gases. Without it, life as we know it would not exist. There may be life in the ocean, but probably not on land in many places. And this is a very famous graph that was first made really popular by Al Gore in a film, but it was well known since the 1980s and really before, that carbon dioxide levels were increasing steadily. The gentleman would go to the top of this mountain in Hawaii where there was an observatory, and he would detect the amount of carbon dioxide and report it, and you see this up and down, and that shows a seasonal variation in photosynthetic activity. In winter in the northern hemisphere, where this observatory is, there's less photosynthetic activity, less carbon dioxide absorbed by plants, higher levels in the atmosphere. Then summer, the carbon dioxide level dropping as it's absorbed by plants and turned into oxygen. So that's why you get this up and down pattern. But this steady rise is irrefutable. Therefore, the scientific consensus, and this goes back now 30 years, and it goes further back than that. Plenty of scientists have known that this was the way it is, and that it's caused by fossil fuels. It's the greatest crime that this was politicized in order to maintain profits for oil companies. That's the only issue. It's the only reason we didn't address this 50 years ago. The consensus is that human activities are adding more greenhouse gases to the atmosphere than would be present without these activities. So what do? Well, you have to reduce the amount of greenhouse gas being put into the atmosphere, because you can see this famous graph, which has this pattern here called the hockey stick, where through the early 20th century, there's a flat line after a bit of an increase through the 19th century with this explosion in the use of coal, then a flat line through the Depression, World War II increases a bit, and then an explosion as the world all becomes addicted to fossil fuels, the hockey stick. Now we have these very tight colored lines going back to World War II, then the colored lines split, and then they disappear. The reason for that is that as you go further back in time, you get a larger and larger gray area, which is an area of uncertainty about the actual temperature of the Earth and how much it might be changing from what was considered acceptable, that's the wrong word, historical averages, right? And again, we're not talking about huge changes in the temperature. Look at the difference. It's only like a half degree up until fairly recently, the 90s. But the problem is that small changes in the temperature reap large consequences. Small changes, big effects. This is a graph that goes further back in time to the year 1000, and you can see very tight data recently. It's clearly dramatic increase, and this stability that had lasted for nearly 1,000 years with some ups and downs, but generally a fairly stable level of temperature suddenly changing. Now, of course, the gray again is the degree of uncertainty. How do we get this data? We can get it from tree rings. We can see in a tree ring, we can see the pattern of tree growth. We know that when we have wide tree rings, we have warmer temperatures, more precipitation. Narrow tree rings, from year to year to year, colder temperatures. We can look at coral growth the same way. They have very distinctive rings which show temperature change in the ocean. We can take cores of ice that can go hundreds of feet down in Antarctica and in the poles, and we can capture gas from the period when the ice froze, when the water froze to become ice. And you capture particular elements which tell you a story about the temperature at the moment the water froze. So there are very solid ways in which we can determine the past temperature. Where do these greenhouse gases come from? Carbon dioxide is natural, but it also comes from what are known as anthropogenic, anthro for humans, human sources. Steady recent increase due to fossil fuel combustion and deforestation. CH4, methane, natural and anthropogenic sources. Methane has always seeped out of the earth, but about half the current emissions are from people, landfills, natural gas, agriculture. Methane is more potent as a heat trapper than carbon dioxide by 30 times, but fortunately does stay in the atmosphere a shorter time. There's also a terrible loop in places like Canada and Siberia where as you warm the earth, and that area of the earth is warming faster than anywhere else, that upper northern latitudes of northern Canada and Siberia, Russia, when you warm that land, you have permanent ice there. If it melts, you get bacterial activity which releases more methane. So the warming creates more warming. The warming creates more warming. N2O, natural and anthropogenic, huge increase in the use of nitrogen-based fertilizers and greased. Nitrogen-based fertilizers for growing food has added this gas to the atmosphere. Other important greenhouse gases, these chlorofluorocarbons, ozone produced in cars at the level of in the troposphere, not in the stratosphere. This is extra ozone. And of course, water vapor, a powerful greenhouse gas. And you can just see that it's gone up, right? So this is very old now. We're well above 400 parts per million now. I think we're about 420. It's just flown up since I started teaching in the last 20 years. So the increase is very dramatic. What are these anthropogenic sources? Well, by country, we release pretty much, not the most. We did for many years the most. Now China, and then the United States, then the European Union, and then you can see this big chunk of what they call the rest of the world. So 3 areas of the Earth are releasing almost half of, a little more than half of the carbon dioxide for the rest of the world. And these are the ways in which it's produced: energy, transportation, building, heating building, cooling building, making stuff, growing stuff, cutting down trees and the loss of trees, and waste. Human waste releases greenhouse gases. Methane from landfills, It's produced inside the stomachs of cows who burp it out, managing pig, chicken, cow manure, wastewater treatment, natural gas systems, which are to recover that gas to use it as a fuel, stationary combustion, just burning that natural gas, mobile combustion, so cars or something else. So you can see methane is released because of human activity. This is a little animation of showing you how the temperature has changed. Now, of course, they've made it dramatic with these colors: blue, cool, right? And then yellows and reds, orange, hot. The opposite of the visible light spectrum, right? And you can see the years on the bottom, and it's getting yellower. And watch the 90s and 2000s as it explodes in red, particularly those upper latitudes. So they updated this. I just didn't find it in time for doing this today. This would be redder now. And it's this area, actually, that is very troubling, because this has got this feedback loop where as it warms, it will cause more warming. And in general, the warming is going to have lots of impacts. So the effects could include ice is melting worldwide, especially at the Earth's poles. This includes mountain glaciers, ice sheets covering West Antarctica and Greenland, and the Arctic sea ice. In Montana's Glacier National Park, the number of glaciers has declined to fewer than 30 from more than 150 in 1910. Much of this melting ice contributes to sea level rise. Global sea levels are rising about 3.2 millimeters, a little more than a tenth of an inch, and the rise is occurring at a faster rate in recent years. Rising temperatures are affecting wildlife and their habitats. Vanishing ice has challenged species such as the Adelaide penguin in Antarctica, where some populations on the western peninsula have collapsed by 90% or more. As temperatures change, many species are on the move. Some butterflies, foxes, alpine plants have migrated farther north or to higher, cooler areas. People are on the move. Precipitation, rain and snowfall has increased across the globe on average, yet some regions are experiencing more severe drought, increasing the risk of wildfires, lost crops, and drinking water shortages. Some species, including mosquitoes, ticks, jellyfish, and crop pests, are thriving. Booming populations of bark beetles that feed on spruce and pine trees, for example, have devastated millions of forested acres in the United States. Sea levels are expected to rise between 10 and 32 inches or higher by the end of the century. Hurricanes and other storms are likely to become stronger. Floods and droughts will become more common. Large parts of the United States, for example, face a higher risk of decades-long mega droughts by 2100. Less fresh water will be available, since glaciers store about 3/4 of the world's fresh water. Some diseases will spread, such as mosquito-borne malaria and the 2016 resurgence of the Zika virus. Ecosystems will continue to change. Some species will move farther north or become more successful. Others, such as polar bears, won't be able to adapt and could become extinct. I'm going to stop with that and go back over these last 4 slides when we continue.